Melbourne researchers are using Australia's fastest supercomputer to simulate for the first time the 3D motion of the complete human rhinovirus, the leading cause of the common cold. Although for most of us, the common cold can be relieved with over-the-counter drugs, rhinoviruses can cause hospitalisation and even death in more than 35% of patients with acute chronic obstructive pulmonary disease. It is also linked to 70% of all asthma exacerbations, which can lead to hospitalisation. Research led by Professor Michael Parker from the University of Melbourne's Bio21 Institute and St Vincent's Institute has led to the creation of the first 3D simulation of the motion of the rhinovirus and how it binds to a new biota antiviral drug.
We've been able to use the supercomputer Blue Gene at Melbourne University to simulate the motion of the virus in 3 dimensions. And what is one of the first is we've been able to do that with a whole virus, including its genetic material inside the virus. So this is a world first.
What's so exciting is really having the capacity to model these biological entities in order to understand how a virus works. Really what we want to do is model the entire virus piece by piece. And for the first time, really, we've been able to do that because we have a large enough computer that's fast enough to be able to do the task. So what we have here is our model of the rhinovirus. So what we're seeing here is its basic components. When we zoom up to the virus, we're actually looking on the inside of the virus. The virus itself is sort of like an egg. You have the outside bit, or the shell, we call it the capsid, and on the inside we actually have the RNA, and the RNA is the infectious part. So once that gets inside our cells, this is what makes us sick.
The research team is working on the newly installed IBM Blue Gene Q at the University of Melbourne, with computational biologists from the IBM Research Collaboratory for Life Sciences Melbourne and the VLSCI, the Victorian Life Sciences Computation Initiative.
The Blue Gene Q is approximately 800 teraflops. That's roughly equivalent to about 20,000 desktop systems. So the Blue Gene actually allows us to do much more complex and larger calculations in a much shorter amount of time. The use of computers is not new in biology. What is new is the level of detail and the complexity of the calculations we can do. That basically allows us to do science in a new way in the 21st century.
It's hoped this research with the supercomputer will open the door for new drug development, saving the lives of many around the world.